Hi everybody, if there was a greatest hits list of popular algorithms, the Fibonacci sequence would be right at the top. It's one of the more famous examples of a recursive algorithm, and we looked at recursion in an earlier video, and it also has more optimized versions of itself that are better than the recursive option. So it has a lot of depth, which makes it great for interviews, programming exercises, and exam questions, and a whole lot more. So in this video, let's learn about what the fuss with the Fibonacci sequence is all about. So let's start at the very top. Let's look at the very boring definition of how we will see Fibonacci presented, and then we'll look at some examples to help make this definition make sense. So a number in the Fibonacci sequence is a sum of the two preceding numbers, and the way this is all kicked off is that we're given the 0th and the first Fibonacci number, and they're both 0 and 1 respectively. And every sequence after that follows this pattern, where it is the Fibonacci number is a sum of the two preceding numbers, which in this case is Fibonacci n-1 and Fibonacci n-2. And so the best way to understand that more is to look at an example. Here we have a very quick table. You can see that we have the Fibonacci, the number we're looking for on the far left, the n variable, and then the value of Fibonacci at that value in the second column, which is highlighted in yellow. And you can see that 0 and 1, the first two numbers, are already given for us. And so, for example, if we're calculating the second Fibonacci number, you can see that the value is 1. The calculation is the sum of the value of Fibonacci 1 and Fibonacci 0, which is the two preceding values, as it turns out, 1 and 0, and it becomes 1. And so to look at this in a little bit more color, let's say, for example, we want to calculate what is the third Fibonacci number. And so in this case, the answer is 2, and that's because the way we calculate it is we sum up the result of Fibonacci 2 plus Fibonacci 1, which is 3 minus 1 and 3 minus 2 respectively. And that is, as it turns out, the sum of the two preceding values of Fibonacci. So you can see that the sum of Fibonacci 3 is the sum of Fibonacci 2 and Fibonacci 1, just as we kind of saw in the calculation field. Similarly, if you want to calculate the fourth Fibonacci number, it is the sum of the two preceding values. So you can see the bright green, 2 plus 1 equals 3, and it's calculated the same way. And similarly, for example, let's say we jump further down the list and calculate the eighth Fibonacci value. It's going to be the sum of the calculations for 7 and 6, and that's going to be 13 plus 8, which is 21. And you can kind of see how the calculation Fibonacci is heavily dependent on the calculations that we made earlier for previous numbers. So the calculation for the 8th Fibonacci number required us to have already calculated the value for the 7th and 6th Fibonacci numbers, which, as you can tell where the recursion comes in, in order to calculate the value for the 7th Fibonacci number, we have to make sure we calculated the 6th and 5th numbers, and so on, all the way up until we get to either 1 or 0, where the calculation has already been given for us, which is just going to be 0 and 1. And so if you had to look at this sort of in this, more of a JavaScript-like approach, you can kind of see it like this. Fibonacci of 0 is 0, Fibonacci of 1 is 1, 2 is 1, 3 is 2, 4 is 3. That ultimately ends up leading to the simplified equation, which is Fibonacci of n is Fibonacci of n-1 plus Fibonacci of n-2, which we saw earlier. And the thing is, if you like recursion, you're going to be very comfortable here, at least in part 1 of this video. And the Fibonacci sequence is also a great example of an algorithm that highlights the limitations of using recursion. We'll see some examples of what makes it very unideal, or not the greatest solution here. And it provides a perfect jumping off point for us to learn about some non-recursive ways and some optimized recursive ways of calculating the Fibonacci sequence, and apply that to other types of computational problems we'll be encountering in the future. Now, before I go further, I should let you know that if you want a friendly and comprehensive look at data structures and algorithms, including our friendly Fibonacci sequence, my book on this topic, Algorithms, Absolute Beginner's Guide, is just what you need. Look for it in pretty much any bookstore, either online or in physical real-world locations. So now let's take a look at the Fibonacci sequence. Let's look at the code for it, because we saw at a high level how the mental model of it should be thinking about how to solve for a Fibonacci sequence. Now the code in many ways reflects that. You can see that we have our function called Fibonacci. We check if the input is 0, and if it is 0, we return a 0. If it's 1, we return a 1, because we know 0 and 1 value, or first values, are provided for us. Otherwise, we just do a recursive call where we return the sum of Fibonacci n-1 plus Fibonacci n-2. Now, the easiest way to visualize this, or at least I think the easiest way to visualize it, is by looking at it in terms of boxes. So let's say, for example, we want to calculate Fibonacci of the third Fibonacci number. We know that the way our code is currently structured, it's going to branch out into the calculation of Fibonacci 2, Fibonacci 1, which is n-1 and n-2, which then will further branch out into helping us calculate the values of Fibonacci 2, which is Fibonacci 1 and Fibonacci 0. Now, when we get to this stage, we know that the values for Fibonacci 0 is going to be 0, and the value for Fibonacci 1 is going to be 1. And so we start resolving the values. So no more recursive calls, we just resolve the call to the value that's ultimately going to be. So you can see that the full resolution of it is 1, 0, and 1 for the branching that came out of Fibonacci 3. And that is, of course, controlled by this highlighted line of code here. We can see that Fibonacci n-1 plus Fibonacci n-2 is the recursive call that we ultimately advertise. So what this means is that we end up adding 1 plus 0 plus 1, which is 2. The third number in the Fibonacci sequence is indeed 2, so we did good here. Now we went a little lengthy in our visual explanation here, but let's speed things up and look at one more example of us calculating the Fibonacci sequence recursively. And this time, let's calculate the fifth number in the Fibonacci sequence will look like. And here you can see a much more elaborate branch. And just like before, the branching follows the same Fibonacci n-1 plus Fibonacci n-2 formula that we looked at earlier, and this keeps branching and creating more children until we get to essentially what I consider leaf nodes of Fibonacci 1 and Fibonacci 0, which of course we know resolve to either 1 or 0 depending on the value. And here you can see for Fibonacci 5, you get to see in this case, like let's see, you have 1 0 1 0 1 1 0 1, which is 1 2 3 4 5. So yeah, so it turns out the Fibonacci value, the fifth Fibonacci number is 5, as it turns out, which is, I think, the correct value as well. So one thing to notice though, right, is the sheer number of recursive calls we're dealing with here. We aren't even dealing with large numbers. What we saw in the previous slide was just the calculating the fifth Fibonacci number, and the jump in recursive calls just between the third number, the Fibonacci sequence, and the fifth number is huge. And if we actually were to calculate that out, where we actually plot the number of function calls for the value of n, or the Fibonacci number we're calculating, notice the growth that you're seeing here, and definitely pay attention to the value on the left side, which is the y-axis, and you can look at the values are going from almost very small numbers until we get to around 15, and then once we start getting towards 20 and beyond, we're in 25,000, 50,000, 150,000 territory. So for example, I have this calculation in front of me right here, the 20th Fibonacci sequence, there are the 20th number in the Fibonacci sequence, there are 22,000 function calls. And if we just go 4 numbers later to the 24th number in the Fibonacci sequence, it's a whopping, get this, 150,000 function calls. That's a lot of calls. The running time of Fibonacci, the recursive version with no optimization, is O to the 2 to the nth power. So it's big O, 2 to the n. That puts it towards more of the high end of how expensive an operation we're performing here looks like. And there are ways we look at how to improve upon this recursive approach in the near future. And before I get too far into it, why is a recursive call so expensive and why do we want to minimize that? So there are 3 things. Function calls require additional memory. They require additional processing time, and then function calls can cause stack overflow errors. We saw about stack overflow errors looking at recursion earlier. All 3 of these things we do not want. And in the part 2 of this video, we'll talk about, go into more detail about these 3 areas and how we can optimize it so that we are still able to calculate really large values of Fibonacci, but not have to suffer the massive growth in recursive calls that kind of put a bound pretty much at the low end of how far we can go before our computers just fall over. So if you have any questions to learn about data structures and algorithms, or just web development in general, the easiest and best place to get your answers is at the forums at forum.crypto.com, where I and others will be happy to help you out. And if you want to keep up with all the content I create, check out all the links below to like, comment, or subscribe to this video, to sign up for the newsletter, follow me on Twitter or X or anywhere else in the social networks that you might find me in, and also the various books that I have that are going for you. And with that, I will see you all next time.